Um, Hi everyone. Today you'll be looking at reduction of ketones. Today is expected to be a very unique lab experience because you won't be doing the lab yourself. Someone else will be doing the lab for you, and uh, you'll be watching a video that shows you how the lab is being done. Basically, be watching from the person's eyes as the lab is being done. Uh, the video also comes with a subtitle. So make sure you pay attention to the subtitle because the subtitle, gives you an insight as to what is going on in the lab because the person won't be saying anything. So pay attention to the subtitle. You can also fast forward, pause and rewind, and, do all sort of things you can do with the normal video. Uh, so let's get started. Okay, so reductions of ketones. So this is actually a slide that was made for spring of 2020. You'll be doing the same experiment, basically the same experiment, and we'll just roll with it. Now, keep in mind that since the lab is based off of what was done in the spring of 2020, the lab is supposed to be a two-part lab where you're supposed to isolate the starting material that you'll be using to do this lab. So some of the explanations you see in the slides and in the corresponding video would assume that, you're starting the experiment from where you stopped the last time. So you can ignore things like that. But other than that, it's all straightforward. Do slideshow. All right. So reductions of ketones. So or reductions of carbonyl compounds. So basically, reduction is basically a reaction where you're adding hydrogens or you're removing oxygens or you're doing both. Addition of hydrogens, removal of oxygens, or addition of hydrogens and removal of oxygens happening at the same time. And usually whenever you do reductions on carbonyl compounds are basically compounds with a C double bond O. Okay, whenever you're doing reductions on a carbonyl compound, you're converting the carbonyl compound into an alcohol of some sort using a metal hydride reagent. So the two of the most common, reducing agents that you commonly encounter in organic chemistry is you have your sodium borohydride, which is a very mild reducing agent, okay? Very mild. And then you have your lithium aluminum hydride, which is a very strong reducing agent. So generally, depending on whatever you want to reduce. So basically what I'm saying is lithium aluminum hydride is very strong. Simply means it can reduce almost anything. However, there are very few functional groups that sodium borohydride can actually reduce. And there are some that it won't work for, it wouldn't reduce at all. So the purpose of this lab is you're going to be reducing a ketone using sodium borohydride, and you'll be monitoring the reaction using TLC. And you've been introduced to TLC. TLC is basically the paper chromatography you did in your chromatography lab. But you won't be doing this yourself. You'll be watching someone do it. So you'll be using the TLC to monitor the progress of your reaction. I'm going to shed more light into that as we carry on in this lecture. So lithium aluminum hydride, as I said earlier, they are not very selective. They reduce anything, they reduce anything in sight. They readily reduce, aldehydes, ketones, esters, amides, carboxylic acids, all into alcohols, okay? Very strong reducing agents. Aldehydes are usually reduced into primary alcohols, ketones into secondary alcohols, esters into primary alcohols, carboxylic acid into primary alcohols, and amides into amines. Okay, so they're very strong reducing agents. Sodium borohydrides, on the other hand, they are less reactive. They are very selective. Selective in the sense that the very few functional groups they can reduce. They can only reduce aldehydes and ketones. They can reduce esters only under, certain special conditions. However, they readily reduce aldehydes and ketones They are ineffective at reducing carboxylic acids and amides. So this is like a generalized mechanisms for metal hydride reduction. So lithium aluminum hydride, sodium borohydride, or any of those type of reagents, this is the mechanism of reduction that you generally see with them. So basically, the hydrides, for the lithium aluminum hydride or sodium borohydride, their job is to provide an hydride. An hydride or a hydride is basically an hydrogen atom that has two lone pairs of electrons with a negative charge on. It's an hydride. So you're donating an hydrogen to the carbonyl carbon of your ketone or aldehyde, as the case may be. In this case, you're looking at the mechanism of, let's see if I can get, laser pointer. So basically here you're looking at the mechanism for reduction of a ketone. So your metal hydride is going to donate an hydride, okay, which attacks the carbonyl carbon, and then you have electrons flow to the top of the oxygen. Normally you form this intermediate with your oxygen atom, which is electron rich now, coordinated with your, your corresponding conjugate base. And then once this is formed, you quench the reaction with water or with an alcohol. Basically anything that can serve as a proton source. Water can serve as a proton source. Methanol, which has an OH group, hydrogen, serves as a proton source. Any alcohol would basically suffice. And basically what the alcohol or water, as the case may be, does is, it adds to the negatively charged oxygen and you end up forming your alcohol. The same reaction mechanism goes for the ester. The hydride is donated to the carbonyl carbon, electrons flow to the oxygen, you have coordination with your the conjugate base of your methyl hydride reagent, and then electron flows back down. So basically this is like an addition elimination type reaction. Electron flows back down and then you lose your your leaving group, and then you end up forming an aldehyde. Then the reaction occurs again, another molecule of your lithium aluminum hydride or sodium borohydride donates an hydride to the said aldehyde now, and then the same process occurs until you get your alcohol. So basically with esters, it's a two-step process where your lithium aluminum hydride, your sodium borohydride, you need 2 molecules or 2 moles of that to actually do your complete reduction to get your alcohol. So yeah, it's the story of the mechanisms. As you're listening to this, ignore the maxi climber behind me with the bags. It's none of your concern. All right, so the purpose of this lab, however, is to reduce fluorinone to 9-fluorinone. Fluorinone, this is the carbonyl carbon right here. It's a ketone. You can see your C double bond hole right here. Reducing it with sodium borohydride, and then you end up getting your alcohol right there. So as you can see, you are adding 2 hydrogen atoms. One is going to come from the hydride that will be supplied by your sodium borohydride, and then the other hydrogen will come from your alcohol, the methanol that you would use to quench the reaction once it's done. And as you're doing this reaction, it's yes, you're learning how to do a reaction, but what's most very important about this reaction is how you use the TLC, the thin layer chromatography, to monitor the progress of your reaction. Because basically, at several time points, you're going to take samples from your reaction and then you develop it to see where the reaction is at. Now, because the starting material is different from the product, you might be asking, how can you monitor this by TLC? You remember from your paper chromatography when you were trying to separate your beta carotenoid from your lycopene, which are 2 different molecules, and they both have 2 different arrows. You can see them on the plate, on your paper. The same thing is going to happen here. Here you don't have a ready-made mixture. Here you're converting one compound into another compound, and as the reaction progresses, you'll be able to monitor by TLC, because the starting material is going to have a different RF. The product is also going to have a different RF. So as you study the progress of reaction, you would be able to see as the starting material is being converted into product at certain time points. So towards the end of the reaction, you should have more product than you have starting material, because obviously that's what you're trying to do, convert the starting material fluorinol into 9-fluorinol. So pay attention to how the reaction is monitored by TLC. All right. Yeah, this disclaimer, the experiment is time sensitive to have everything ready before your reaction begin. Yeah, you're not doing any reaction, you're just watching. So enjoy. So basically this is the procedure, and just follow through the procedure. You're starting with 200 milligrams of 9-fluorinol. Pay attention to 200 milligrams of 9-fluorinol. Pay special attention to this. This is the amount you're starting with. Okay, so pay attention to that. 200 milligrams of 9-fluorinol that you isolated from last week, you didn't do that. So, but let's just pretend like you did. And then 4 mils of anhydrous methanol, and prepare 2 TLC plates to track the time points of the reaction, which is very important. The TLC plates will generally look like this. As you can see, you have 4 spots on each plate. And as you can see, this is how you're gonna, the legend for the spots. You have 1, which will be your fluorinol starting material. 2 will be your fluorinol, which will be right here. And then, 3, 4, 5, 6, 7, 8 are gonna be time points for your experiment. Okay, and this is just for tracking your experiments as as it progresses. Over 8 time points, but this looks like 6 time points. Anyway, so yeah, you label your test tubes as, so you have to make a standard solution of your pure fluorinol and the expected product you expected to get, your fluorinol, your 2 standards. Standard 1, the fluorinol goes on spot 1, the fluorinol goes on spot 2, and then all the subsequent spots will be your time points as the reaction progresses. So once your fluorinol is dissolved in the methanol, then you add your sodium borohydride. Okay, if you add your sodium borohydride, you take a sample spot at position 3. That's your time 0. Okay, the reaction starts stirring at 30 seconds. You take another spot at position 4, 60 seconds, 120 seconds, and then up to 600 seconds. And once you have all those spots up to 600 seconds and everything is dry, you run your plate in DCM. So your mobile phase is dichloromethane, also known as DCM. You run your plate like you did with your first your chromatography experiment. So after all this is done, of course, you're going to get a nice result from that, which you would have to interpret. Now, take note that you will be, what we want you to see is your starting material being converted into product as the reaction progresses. The reaction may or may not go into completion. What I mean is the reaction, you might not get to a point where you will just get exclusively product. You might still have some starting material. But at the end of the day, you should be able to see the intensity of your starting material fade over those time points and the intensity of your product increase over those time points. And that tells you that the reaction is being progressive. It's moving the way you want it to move. Okay? All right, so after you've done that, you have to isolate your product. So you have to transfer the reaction solution to 10 ml flasks, add approximately 2 ml of water, and then you recrystallize. So recrystallization is a purification process. It's very important that you know what recrystallization is, especially now that you guys are not doing the experiment yourself. So recrystallization is a purification process that allows you to remove impurities from the products you're expecting from a reaction. Okay, so how this is done is you're starting your product, the pure compound that you're expecting is soluble in the chosen solvent when it's hot. Okay, and then as it cools back down, it crashes out, it crystallizes out of the solution as a pure compound. So what I'm saying is when you have a solid mixture or you have a compound that's a solid, and it has a little bit of impurities in there, and you want to recrystallize, your impurities have to be soluble in the solution you want to recrystallize in, both when hot and when cold. However, the main product, your pure compound you're trying to get, is only allowed to be soluble in the solvent when it's hot, not when it's cold. So you have to pour your solvent, which is water in this case, into your mixture, and then you eat the mixture slowly until everything dissolves. And then once everything is dissolved, you leave it to stand at room temp, or you put it in an ice bath to slowly cool down. As it cools down, your pure product is going to start to crystallize out, and your impurities will remain in solution. And once this is done, you can filter off your pure crystals, and there you go. That's your recrystallization process. It's very important to know that for recrystallization to work, the product you're expecting, your pure compound, should be soluble when hot and insoluble when cold. Your impurities should be soluble when hot and when cold. That's only how your recrystallization process can work. All right, so after you've filtered off your product, which is your 9-fluorinol, now you have to leave it in your bench for 24 hours to dry off. And that's because you have to take the weight of the dried product once it's done. If you wait immediately, you still have some solvents in there. It's not going to be totally dry. It's going to be dried, nice and, crispy. And then you can weigh your stuff on a weighing balance. And the goal of this is to calculate your percentage yield. The goal of this is to calculate your percentage yield, okay? And what is your percentage yield? Your percentage yield is basically the percentage of the product that you isolated relative to the theoretical product you're supposed to isolate. I'm going to explain what I mean in a moment. So I'm going to teach you guys how to calculate your percentage yield, which is a very important thing you need to know how to do. I'm trying to share screen. All right. So basically, to calculate your percentage yield is equal to your actual or experimental weight. So basically, you're looking at the actual amount of product you isolate from the experiment and over the theoretical weight, also in grams. Basically, so your theoretical weight is, we are assuming that you have 100% conversion of your starting material into product. So that's your percentage yield. How do you get your actual weight? It's very simple. Remember, you have to weigh your product after 24 hours. So basically, the weight you get from that, the weight of the product on the filter paper minus that of the empty filter paper, that would give you the actual weight that's isolated from the experiment, your experimental weight, okay? The theoretical weight is where it gets tricky, and that's where a lot of students get lost. And if you don't get this correct, you're not going to get your yield correct, and you lose points for that too. So make sure you pay attention to this. So you're converting fluorinone to fluorinol. Now, all things being equal, if the world was right, when you start this reaction, if you start with X moles of fluorinone, if all things were right, you should get what? X moles of fluorinol. You are assuming 100% yield, okay? Because 1 mole of this will give you 1 mole of this from the equation you have in the slideshow that I've just shown you guys, okay? So X moles will give you X moles of your 9 fluorinol. Now, you basically have to convert this into mass. And to do that, you need the molecular weight of this. However, to calculate the number of moles of fluorine you started with, remember I told you guys, pay attention to the amount of fluorine that you started with. Now, according to the slideshow, you're supposed to start with 200 milligrams of fluorine. However, when you're looking at the video for the actual experiment, you need to use the exact value that the weighing balance gets recorded for. So the person you might be asked to start with 200 milligrams, but the person might end up weighing 206 or 207 or 210. Make sure you use that actual value to calculate your theoretical weight. Okay, so let's assume the person actually weighed 200 milligrams. You have to convert this into moles. Don't forget that this is a milligram, so you convert this into grams first, and then using the molecular weight of fluorine, you convert the 200 milligrams of fluorine into number of moles of fluorine. Now, whatever you get for that, that would be the number of moles of 9-fluorinol that you are expected to get, all things being equal, your theoretical moles. Okay? And once you get that, you can convert your X moles into mass of fluorinol. Okay? And you use the molecular weight of fluorinol to do that. I'm sure you guys are familiar with your stoichiometry, so I will let you, figure this out. So once you have the theoretical mass of your fluorinol, you can slot it back into this equation up here, and there you go. You can calculate your percent yield now. If your theoretical weight is not correct, your percent yield will be wrong. So make sure you show all these workings in your write-up when you're done. Okay? I'm gonna come again just to give you a brief overview. Percentage yield is actually equal to the actual weight you get from the experiment. So you have to get the weight of your filter paper with your product after 24 hours, get that, and then minus the filter paper when it's just empty. That will give you the actual weight from the experiment. You get that from the experimental video you watch. For the theoretical weight, you need to calculate that yourself. And to do that, you need to know the amount of fluorine that the person doing the experiment actually started with. The exact value, it might be 200, you are supposed to start with 200 milligrams, but it might not be exactly 200 milligrams. You convert that into moles, and whatever moles you get, you should get the same, theoretically, number of moles for your product. Okay? And now that you know the number of moles of your product, your 9-fluorinol, you can multiply that with the molecular weight of your number of moles, and that will give you the actual theoretical mass of your fluorinol. And you can slot it back into the equation up here and calculate your percentage yield. For your melting point, the same story goes. You the person will do the melting point. You get a value for your melting point and you compare it to that of pure fluorinol. How do you get the melting point of pure fluorinol? Internet, ask Siri or ask Google, I don't know, Alexa, they'll tell you. And then you write up your post-lab report, answer your questions, write your discussion, and then you're good. You know how to reduce ketones now on video. Good luck, guys. Enjoy. Peace.